Good morning, my dear friends, and welcome you all to the concluding day of this prestigious international conference on VLSA design and embedded system. I'm sure you must have enjoyed all these last 4 days of great show, starting with first 2 days of tutorials, followed by the 3 days of paper presentation and various technical tracks, multiple keynotes, panel discussions, and here comes the last but not the least day, and we have a special agenda for all of you today for this session. So we are starting this day with a very unique session today, which is Student Research Forum, and this is one of the key forum for VLSA Design Conference. And to start this session, what not to have a great talk by our invited speaker here, Professor Devdip Mukhopadhyay from IIT Kharagpur. So Professor Devdip don't need any introduction. He's a known face, globally in VLSI semiconductor security cryptographic community. But let me take this pleasure and honor to welcome him to the stage today and briefly introduce about him. And I would say that we can write books about his achievements and all the accomplishments he has earned all these years so far. But let me briefly introduce Professor Devdip. So Professor Devdip is currently a professor in the Department of Computer Science and Engineering at IIT Kharagpur. And at Kharagpur, he initiated the Secured Embedded Architecture Laboratory, known SEAL, SEAL, with a focus on hardware security. He had worked as visiting scientist at NTU Singapore, visiting associate professor of NYU Shanghai, assistant professor at IIT Madras, and visiting researcher at NYU Tandon School of Engineering, USA. He holds a PhD and MS and a BTech from IIT Kharagpur. So what alumni all these years, from bachelor's to master's to doctorate, and now producing many more doctorate students for the upcoming generation. He has written multiple books, and as I said, the list is long, and he has written more than 250 papers in the peer-reviewed conferences, journals, and collaborated with several Indian and foreign organizations. He has been on the program committee of multiple journals and international conferences. Mr. Professor Mukhopadhyay is the recipient of the prestigious Shanti Swarup Bhatnagar Award 2021 for Science and Technology, the Khosla National Award from IIT Roorkee, and is a fellow of the Indian National Academy of Engineers. He was awarded the DST Fellowship for 2015-2016 Data Security Council of India Award for Cyber Secure Education, and multiple other such awards, books and papers and whatnot. So it is a true honor, privilege, and for me personally and for the whole conference team to start this research forum, student research forum, from such a a great researcher among such. So we'll get started with his invited talk, and post that we'll have the other research student research forum paper presentations to be done. So welcome Professor Devdip to VLSID.
So thanks, Preet, for your kind introduction, and thanks to all of you for inviting me. So I will try to share my screen first so that my slides are visible. Just kindly confirm that it is visible.
Yes, if you can go on full screen mode, please. Great.
Yeah.
Thank you.
So thanks again. So I will try to give like a perspective on on research around this wonderful topic of VLSI that we essentially are all very excited about. So I will not really be talking about a specific topic which is on security, as Preet already mentioned that I essentially work in the topic of hardware security, but I will try to be like more generic in today's quick talk, and largely try to kind of cater to the various kinds of research topics that are growing or emerging around this topic of VLSI. So therefore, the title of my talk is very large scale integrated research, which is I think very getting more and more prominent nowadays when we see so many interdisciplinary topics which essentially can improve VLSI, and at the same time VLSI can also have a positive effect on these research topics. So I mean, like all probably like conferences in VLSI have this interesting discussion on Moore's law, and it is interesting that how it has driven like your VLSI or our VLSI technologies to like from single transistor integrated circuits to more complicated devices where like billions of devices are being packed together. And for us, right at this point, we understand that this integration is pretty obvious, kind of we like often take it for granted. But they like this immense progress in VLSI has happened due to like contributions of various researchers around the world of understanding how we can like cram more components into the integrated circuits and still ensure functional correctness. So it is kind of, I would say, like quite an achievement to see like very small devices now like housing several transistors together, several devices together, and performing things in a meaningful fashion. So we have seen the evolution of like various technologies like like mobile phones and so on, which has really amazed us over the years. So I would try to kind of in today's talk quickly like talk about this like this buzzword of machine learning, which is like which is not really new. I mean, this is a point that I would like to kind of emphasize is, although like we hear machine learning and its impact on our present day society, right? Essentially, machine learning is not really new because like it was there even before. But the one of the reasons why like we have a rebirth of machine learning is because of the development of our present day architecture and hardware. So I would say that the reachability and the acceptability of machine learning has very strongly been benefited from the growth of VLSI technology. Okay, and due to the various inherent parallelisms that our VLSI circuitry can achieve, we essentially have now the capability of performing data processing on huge volumes of processing power, and therefore, right, we have got a plethora of hardware devices which essentially, depending upon various applications, depending upon various performance and functionalities, we essentially can we have those like inherent hardware circuits which essentially can enable this technology of machine learning. So in this illustration, which is present over here, you can observe that there are a various range of hardware circuitry or VLSI, like circuits which has evolved. And the interesting thing is that there is no one hardware rule all platform. So depending upon the various kind of applications, depending upon the various performance and also the functionalities, we will probably like be ranging over the CPUs, the GPUs, TPUs, FPGA solutions. So all of them, right, will have their own, like I would say pros and cons, and that actually I believe like makes the study so interesting. So if you are like studying machine learning nowadays, you will be probably not very agnostic about VLSI. And likewise, I would also like to mention when you are studying VLSI, right, essentially because we know that VLSI has got so many challenges in itself, and it has always been enriched by the technology around them, and one of them is machine learning. Okay, so this brings me to this question, that can VLSI itself benefit from machine learning? So we know that VLSI CAD is always evolving, and it essentially has got to and interesting, like it has got many common problems with machine learning. For example, it has to handle big data. For example, like because of the Moore's law, we know that we are now dealing with billions of devices together, and that has led to an exponential amount of complexity increase of data handling. And that means that we need a structured approach for controlling complexity, right? And the usual way of how like complexity is handled in VLSI is by like having different levels of abstraction. So for example, we have an RTL abstraction, we may have a transistor level abstraction. So abstraction helps us in controlling complexity. Okay, but at the same time, right, we also need computational efficiency. And computational efficiency means that the compute that we are doing essentially has to be done in a proper, I mean, there has to be, the optimizations being done suitably, the synthesis being done suitably, and so on. So you will find that all these things, right, all these attributes are essentially shared problems with machine learning. And therefore, right, there can be, various applications of machine learning into the usual problems of VLSI as well. For example, you may find machine learning being applied for lithography and physical design. You may find it for, physical verifications, mask synthesis, physical designs, manufacturing, yield, reliability, even automatic generation of assertions for RTL designs, right, can be enriched by various data manipulation techniques, like probably, assertion mining and various kinds of, techniques may be apt for such kind of purposes. Machine learning has also been, used for analog designs. And here is a very interesting, reference. If some of you are interested, you can see where machine learning can, be applied in a beneficial manner for VLSI. So therefore, there are, I would like to kind of summarize this point by saying that VLSI has benefited machine learning, and at the same time, machine learning also has, benefited VLSI and is going to, benefit even in the future. So the next point that I would like to kind of rather, raise is, the growth of VLSI essentially has also been, kind of synchronized with, various devices being, interconnected. So we now talk about Internet of Things, Internet of Medical things, and so on. That means like we are essentially now dealing with not only like few devices, but, several devices being communicating with each other. And this power of control and command also brings us to this question about security and trust. Because of the growth of VLSI, I mean, VLSI right now, right, is nobody, we know that, when you are talking about, say, an IP design, or you are talking about, the corresponding fabrication, you are talking about, the entire process of the design conception to the realization in some fabrication unit is kind of done in a very heterogeneous manner. So it is kind of distributed across the globe. And therefore, VLSI is really trusted. Okay, and there can be several array of, probable vulnerabilities that essentially makes this very interesting subject of what we call as hardware security, which is one of the areas that I work on. For example, like if you are taking a very strong cryptographic algorithm and if you're implementing it on a VLSI chip, there are questions like that whether the power consumption of the device is revealing the secret key. Okay, so here is a trace. For example, you can see of a power of a trace, obtained from a microcontroller, which is, say, processing AES kind of crypto system. So AES is a very strong crypto system adopted worldwide. But if the VLSI is not done suitably, that means if the chip design is not done suitably, then the implementation footprints on the power consumption can reveal your secret keys. And even the strongest of mathematical algorithms cannot really protect them. So therefore, it's a huge concern. And if all of us are carrying, some smart card or the other, you will be assured that they have protections against such kind of attack vectors. Likewise, when we talk about, several devices being communicating with each other, there are always questions of what we call as authentication. So you need to kind of ensure that the device is indeed the correct device that you are communicating with. And this brings us to this exciting domain of what we call as physically unclonable functions, or puffs. So VLSI essentially, and I would say rather the uncertainty of VLSI has been suitably applied for such kind of security solutions of developing what are called as puffs, true random number generators, and so on. So the idea of puffs is that if I take the same circuit and if I implement them across different devices, and now if we extract out the responses, then you'll find that the responses are statistically independent. So this essentially means that you essentially can use the responses as identifiers. You can build protocols and so on. But at the same time, right, you also need to kind of understand the attack surfaces and do suitable, modifications in the design. The third point on security that I would like to kind of emphasize is that our processors or computing systems have been largely developed with performance in mind. Over the last 20 years or so, we have been developing several artifacts like the cache memory, branch predictors, and so on, primarily with performance in mind. But these essentially have opened up avenues for various kinds of attacks, So some of you have heard about these attacks called Spectre and Meltdown. These are examples of where, like a simple performance, I would say, accelerating, technique, which are called as speculative executions, were exploited by adversaries to reveal the secret key. And therefore, right, there are often, like discussions about, like say winding back 20 years of the evolution of our computing systems, keeping security in mind. So therefore, the point is like the security in the context of VLSI design and in general hardware design is becoming more and more, like important, and is essentially, like now kind of, it's an open problem of understanding how do you really, like ensure that your designs are secured, keeping security as your primary design objective, along with other objectives as well, like power, performance, and so on. So I would like to also kind of mention that there are things like reliability issues of, like memory chips, which were called as rowhammer bugs, essentially also have been exploited by adversaries. People also talk about, like applying various kinds of imaging devices which were probably not really being used for IC design at some point, till some point, are now being used for Trojan detections and, like various kinds of security, research. So finally, right, I would like to conclude this, like quick talk by saying that there are several walls, as we know, in the context of VLSI. For example, if we talk about the classic von Neumann architecture, which essentially is probably still, influencing most of our computing devices. And there are several walls, like we know of the memory wall being one of the most, well-studied walls, because of the fact that although our processors have become strong, I mean, much faster, our memory is not so fast. And therefore, in order to bridge that, we have got different levels of cache memories and so on. And while this can have potential security issues, as I was mentioning just before this, at the same time, it also is a major, like limitation to, like having or enabling various kinds of technologies, like, even machine learning, or, like there can be several kind of applications which are being developed in this context. When we talk about data-centric designs, I mean, this essentially takes us to this very exciting world of looking at, like further to our CMOS technology, because we know that our CMOS is also reaching its physical limitations because of its high static power, lessened reliability, and so on. And this brings us to this very exciting topic of compute in memory, which tries to kind of, like interweave the processing unit and the memory at the same physical location. So there are various examples of this, for example, memory stirs, RERAMs, and so on, which are being studied in this context, and essentially tries to kind of look at new paradigms of computation to overcome the classical walls in our, like good old VLSI design. So in summary, what I would like to mention is that uh, we have seen several, like artifacts being developed. For example, we have talked about, we have seen that VLSI has really, like grown and emerged over the years. But at the same time, right, there are also other technologies which are growing around us. For example, machine learning. There are other concerns that are growing around us, like security. And therefore, it is very important at this present times, right, to understand that we are not living alone. We essentially have to do VLSI research, but at the same time, the emphasis on interdisciplinary research is probably much more than the yesteryears. So with this, I would like to stop this quick talk, and I would be very happy to, like address any questions.
Thank you very much, sir. Very interesting talk, sir. So, Professor Devdeep is among the few researchers in the country which is working in the area of hardware security, and which remained a topic of interest for not only the strategy organization but also the government sector. So I was just wondering, I mean, what are the benchmarking standard methodologies in the industry to certify your development? For example, we have been hearing a lot about the PSA from ARM, or Common Criteria for certifications. So what are the methodologies that is being used in the standard industry frameworks for testing your design against the security hacks?
Yeah, I mean, thanks. That's a very important and I would say pertinent question. And of course, like I mean, the quick answer to this is that there are, like different levels of certification that have evolved. Like for example, from I would rather say, like which are more looking at the classic software and hardware security solutions. But at the same time, right? I mean, you will also be seeing that nowadays when we talk about the security attacks which target the hardware in particular, like the side channel attacks, or like such kind of attacks which essentially compromise the hardware, essentially are getting more and more incorporated into the common criteria and also the FIPS in general. So I would say rather that this is a continuous process, and although the standards are not really like being kind of very well understood, and they are still evolving, but you will find that more and more they are getting incorporated into the common criteria. So I would say that there are, for example, nowadays some, like for example, like maybe 10 years before, right? I mean, to understand whether a crypto device is secured against side channel attacks, you would probably be like doing an actual evaluation to understand that whether the design is vulnerable to side channels. But nowadays there are like very interesting tests which have been evolved. For example, there is a test which is called as test vector leakage assessment, which is called as TVLA, which essentially tries to take a device and tries to give different levels of input to it, and then apply statistical hypothesis testing to understand whether the design is vulnerable against side channel attack. So it will basically tell you whether there is a leakage or there is a leakage or not. So it's a kind of a yes no test to kind of say that there is a potential leakage. So these kind of tests are now getting more and more incorporated. So I would say the side channel part is probably, like I would add on to this, that the side channel part is probably well understood nowadays, but the faults are really a big concern. Like like probably you have heard about recently Intel deprecating the Intel SGX, for example. And one of the primary reasons was Plunderbolt, which is essentially trying to tinker with the voltage frequency scaling and doing a fault attack. So fault attacks are a real menace because it's very hard to model them in general, and because you really do not know how the adversary can instantiate a fault, right, and can exploit.
Right. And so one more question. I mean, we all know that nowadays many techniques for the physical design and backend design are being introduced by the EDA vendors, which are mostly automated, right, based on ML and AI techniques.
Right.
So compared to, manual design, what are the security concerns?
Yeah, that's a very good question, actually.
Automated processing in the backend physical design.
Yeah, that's that's a very good question. I mean, many of and this is something that we are also studying very closely, trying to understand the optimizations that are being done in the CAD tool, the high-level synthesis optimizations, or the physical design optimizations, whether there can be potential security implications. And it turns out that there are security implications, right? And because you may think of that, suppose, let me talk about a very simple strategy to protect against say side channel attacks. Okay, so one of the techniques that are being done is by what are called as masking. So masking means like you try to randomize your computations, and you try to kind of ensure that the computations are independent about the actual data. But then when you are applying your standard CAD tools, the CAD tool may do some kind of optimizations which will lead to like revelation of your actual, essentially will lead to the unmasking of your data. So therefore, right, I think it is a very important concern which you raise, and we need to kind of either come up with like a new CAD tools, or essentially like I would say plug and play CAD tools. Of course, like we cannot denounce the the CAD algorithms that have evolved, but we need to kind of augment them with security awareness. So I think that would be the direction to go.
That clarifies, sir. So I don't see any question in the chat window, if I am right. So in case we are not, if there is any question, you can please post in the Q&A. You can definitely reach out to Professor Devdeep separately also.
Sure, yeah.
And no questions, yes. So then I think, sir, we may end this talk from Professor Devdeep, and we can definitely reach out to him for any questions separately also. And thank you very much, sir.
Thank you.
Forward for more of your guidance in this area.
Thanks.
Very few experts are working in this area, sir. So thanks for enlightening us. Thank you very much.
Thank you.
Thanks for your time, sir. So with this, sir, we move forward to the Student Research Forum, which is an integral part of the VLSI Design Conference, which is organized every year as part of this conference to encourage the bachelor's, master's, and the PhD students who have either completed their thesis in the last 12 months or who are about to complete their thesis. and wish to present their work in the broad audience to get the feedback from pioneers and the domain experts. Now, this year, the VLSI Design Conference, being virtual in nature, received a great response from the students with the numerous submissions, which actually made the job of the reviewers really tough. And however, after a number of blind reviews at multiple levels by the various experts, the most interesting, promising, relevant and state-of-the-art work by these students have been selected for the presentation today. And there are 4 presentations back-to-back lined up of 20 minutes each, which will be followed up by Q&A session. So looking forward for the participation from all of you to not only ask the questions to the presenters, but also guiding them towards their work. So we have the first talk lined up from Nitanshu Chauhan from IIT Roorkee, who will be talking specifically on the impact on polarization switching on hysteresis-free and hysteresis-based ferroelectronic FET. And we all know that FET layer, which is promising oxide layer, is being used for designing not only the low power hysteresis, but also employed to design and the non-volatile memories and some customized analog and digital circuits. So let's hear to the talk of Nitanshu Chauhan. The co-author of this talk is Professor Sudip Das Gupta and Professor Anand Bulusu from IIT Roorkee. So you can ask your questions in the Q&A session, which will be taken up after the talk. Thank you very much. Nitanshu, yeah.
Good afternoon, everyone. My name is Nitanshu Chauhan. I am from IIT Roorkee, and my topic of presentation is impact of polarization switching on hysteresis-free and hysteresis-based ferroelectric FETs. These are my table of contents. Introduction, impact of polarization switching on hysteresis-free ferroelectric FET, which is basically NC FET. In this one, I have covered negative differential resistance in the output current characteristic of NC FET, positive to negative differential resistance transition in NC FET, impact of trap-induced performance degradation on MFI's NC FET, impact of dielectric phase on the performance of NC FET, impact of dielectric phase on hysteresis-based ferroelectric FETs, list of publications. So to begin with the introduction, why NC FETs? As we all know that power, performance and reliability are the primary concerns of any semiconductor design industry. And as we are scaling down the transistor length, lots of short channel effects are coming into the picture. So what are the solutions? We can categorize the solution into 2 subcategories. First one is conventional device architectures. In this category, we have MOSFETs, FinFETs and nanoswitch FETs. And just in the second category, non-conventional device architectures like tunnel FETs and NC FETs. The conventional device architecture suffers from the Boltzmann tyranny of 60 mV per decade. That means substrate slope cannot be lower than 60 mV per decade. But in the case of non-conventional device architecture, these devices like tunnel FETs offers very steep substrate slope, but on the cost of low on current. And due to this one, the tunnel FETs cannot be utilized for high performance applications. While in the case of NC FETs, this device not only offers very steep substrate slope, but it also shows very high on current and smaller off current. And due to this one, these devices are the better replacement of all these devices, and it can be used for low power high performance applications. And negative capacitance, the combination of nanoswitch FETs could be a futuristic device architecture. Along with this one, the ferroelectric FETs is also utilized in memory applications where it can replace phase change memory and resistive RAM memories. So these are my conclusive research objectives. In this one, I have covered physical explanation of negative differential resistance for metal ferroinsulator semiconductor NCFDSOI, its mitigation using proposed NCFDSOI. Physical explanation governing NDI to PDI transition. A methodology is also proposed for realizing the analog amplifiers in NDI region of output characteristic. Study of traps at different oxide interfaces. Individual and combined impact of traps on device figure of merit such as substrate slope, on current, off current, threshold voltage for NCFDSOI. Impact of dielectric phase inside the ferroelectric layer for NCFDSOI FET. Impact of dielectric phase on the memory window for ferroelectric FETs. So this is my calibration of Landau parameters for MFIM capacitor. and this is the calibration of baseline FDSOI. Now, what is negative differential resistance? As we increase the drain voltage, my drain current decreases, and due to this one, the slope of IDVD shows a negative, and this negative slope can be called as negative differential conductance or negative differential resistance. This negative differential resistance can be subdivided into two kind of factors: GDS1, which is dominated by gradient of inversion charge with the VDS, and GDS2, which is dominated by the gradient of electron velocity with the VDS. But primarily, NDR in MFIS is dominated by the gradient of inversion charge with the VDS, since electron velocity saturates at higher VDS. The impact of NDR also analyzed in the previous work as well. In this one, that the explanation is provided for metal ferrometal insulator semiconductor, and that explanation is not valid for metal ferro insulator semiconductor based devices. For the first time, we have explained this NDR effect for metal ferro insulator semiconductor based devices. Along with the negative differential resistance is not suitable for analog applications, so we came up with the idea in dividing the box layer into two sub layers, and upper part of the box layer is working in the NC region, and due to this one, the bottom surface potential has been increased, and higher inversion charge is available in the channel, and due to this one, the gradient of inversion charge has decreased, and our current characteristic shows no NDR effect, and that's why this characteristic can be useful for analog applications. Not only that, the proposed device also shows very high on current as compared to baseline FDSOI. With the help of proposed device, we have also designed the current mirror. In this one, the output current is only shows 2.3% variation with respect to the reference current, while we are varying the VDS from 0.4 volt to 0.8 volt, while the baseline NC FDSOI device shows 27% variation in the output current with respect to reference current. And due to this one, these devices shows the VDS independent current mirror characteristic. These are the key research outcome of this work. First principle explanation of NDR in MFIS and CFET. A novel idea of placing a FE layer in the box of FDSOI mitigates the undesirable NDR effect. The proposed device shows 2.23 times higher on current as compared to the baseline FDSOI. It also offers 47 times higher intrinsic gain as compared to the baseline FDSOI. This work has been published in the IOP Nanotechnology. The output characteristic of NCFET also shows NDR to PDR transition. In this one, for the first time, we have explained this phenomena, and we found that for a fixed gate voltage, if we increase the drain voltage in the steep switch PE curve, the polarization reaches to a metastable point, and beyond that point, the capacitance offered by the ferroelectric layer is positive. And due to this one, the impact of drain voltage over the channel has increased, and the conduction energy shows a planar MOSFET kind of effects. In this one, as we increase the drain voltage, the conduction goes down, and due to this one, we can see the NDR to PDR transition impact in the CBE curve, where the potential drop in the ferroelectric layer has been changed, while we increase the drain voltage from 0.6 volt to 1.1 volt. Along with this one, the NDR to PDR transition range can be modulated with the help of backbody bias, since backbody bias changes the threshold voltage. Conventionally, we know that the NDR region and the NDR characteristic is not suitable for designing amplifiers. So for the first time, we have provided the novel design guidelines. In this one, we can utilize the NDR characteristic of NDR of the output characteristic. Conventionally, we know that if R not equal to infinity, the total gain offered by the common source amplifier would be equal to minus GM into RD. But in the proposed method, if my load resistance is smaller than the driver resistance, and the driver resistance is negative, the total output resistance offered by the system would be greater than RD, and thereby we can achieve higher gain. And in this one, we have utilizing the NDR region of output current characteristic, and we can see from the figure as well. If we bias the transistor in region A, the gain offered in the region A is higher than the other two cases, and that gain can also be modulated with the help of backbody bias, since backbody bias modulates the NDR to PDR transition range. We have also tested the performance of NCFET in the presence of traps. In the case of silicon SiO2 traps, NCFET shows lesser performance degradation as compared to baseline FGSOI, and it also shows improvement in this one as we increase the ferrotic thickness because it offers higher gate control. But the picture becomes opposite in the case of HFO2 SiO2 traps or bulk HFO2 traps. In these two cases, the polarization decreases as we increase the trap concentration and polarization switching happens, and the picture becomes more worse as we increase the ferrotic thickness because the trap concentration increases. We have also analyzed the combined impact of bulk HFO2 and silicon SiO2 traps on the performance of NCFGSY and bulk and baseline FGSY, and we found that for a smaller thickness of ferrotic layer, the NCFGSY shows performance immunity as compared to baseline FGSY since the trap concentration inside the bulk is smaller. But once we increase the ferrotic thickness, the total trap concentration inside the bulk increases, and due to this one, it dominates over silicon SiO2 traps, and NCFET shows higher performance degradation. These are the key research outcomes. For similar oxide thickness, NCFGSI is more immune to performance degradation as compared to baseline FGSY. If the ferrotic thickness increases, impact of bulk HFO2 trap increases, and polarization switching happens. Due to this one, NCFGSI shows higher performance degradation, and therefore it restricts for using higher ferrotic thickness for optimizing the performance. The entire ferrotic layer cannot be a ferrotic. Sufficient amount of dielectric phase always present in the ferrotic layer in terms of monoclinic phase or tetragonal phases. So we have analyzed the impact of dielectric phase on the performance of NCFET, and we found that as we increase the dielectric phase percentage along with the increment in the ferrotic thickness, the NC state become voltage sweep direction dependent, and this is because of the ferrotic grains which are neighbor to the dielectric grains. In order to maintain the directional field in the ferrotic grain which is near to the dielectric grain, the total polarization of the ferrotic layer has been changed, and the net polarization is majorly determined by the ferrotic grain which is neighbor to the dielectric grains, and due to this one, the complete ferrotic polarization becomes direction dependent. This can be seen from the CFE versus VG curve. In this one, at VG equal to 0 volt, we are getting two polarization states which is due to direction dependency, and this direction dependency can also be seen from the transfer current characteristic of NCFGSY. In this one, at the 50% of dielectric phase, as we increase the VG from 0 to VG value, the current characteristic shows different value as compared to the current value once we decrease the VG value from higher value to lower value, and due to this one, it shows direction dependency. So the previous works have been published in the IEEE Transactional Ferroelectrics, IEEE TED, and IEEE IRPS conference. So along with this one, we have also analyzed the impact of dielectric phase on ferrotic FETs, hysteresis based ferrotic FETs. In this one, we have calibrated our work with the experimental data, and as we increase the ferrotic thickness or as we increase the dielectric phase, total memory window has been decreased. We can see from the figure as well, as we increase the dielectric phase, total memory window decreases and variation in the memory window also increases. So from this one, we try to find out the best possible and worst cases, and we found that when the ferrotic grains are uniformly distributed in the ferrotic layer, that case provides the best memory window, and when the ferrotic grains are at either side of the ferrotic layer, in this one, no current path is available, and effective channel is being dominated by the or being governed by the dielectric phase, and this one it provides the worst memory window, and it results in memory window closure. These are the key research outcomes. Dielectric phase in the FE layer and its randomization with increasing TFE cause voltage sweep direction dependent NC state. Dielectric phase in the NCFGSY results in steeper substitute slope but direction dependent substitute slope for NCFGSY. Ferrotic FET is resilient to the dielectric phase up to certain percolation threshold. The grain density should be increased in order to suppress the variation in the memory window. Leakage path results in memory window closure. So this work is published in IEEE EDL, Electronic Voice Letters. These are a list of publications. I have published 9 journals. 15 conferences. This is our team. Dr. Anand Datta, Dr. Kaini are my mentors. Professor Sujat Das Gupta, Professor Anand Bulus are my supervisors. These are the my team members. Acknowledgement. I would like to thank IIT Roorkee, NIT Uttarakhand, Department of Science and Technology, Government of India, Science and Engineering Research Board, Government of India. Thank you. I am available for the questions.
Thank you, Tanshu. So very nicely demonstrated, and IIT Roorkee is definitely the lead model for the device modeling in the country. So very nicely demonstrated the impact of traps in the dielectric phase present in the ferroelectric circuits. What is your understanding and opinion on the impact of these traps on the negative capacitance-based PMOS FETs?
Sir, actually, once we are having these steps, so these steps individually impact. Am I audible, sir?
Yeah. Yes.
Yeah. So if these steps are present in the PMOS, so individually they impact in a different way as compared to NMOS. Like in the case of bulk taps, if you are having bulk tap of same charge, like negative or positive, if you are having negative charge, then it will strengthen the PMOS characteristic. But if both the taps are present, like positive or negative, both are present, and if positive dominates, and in that case, it will again degrade the performance. So based on the quantity and the charge on the taps, that will degrade the performance.
Okay, and what is the why NDR is not good for the analog circuit designing? You explained about it.
Yeah, so since if we know NDR is negative differential resistance, so if we go for a small signal model of any transistor, we found that if there is a negative resistance available, so the pole of the complete system would be in the right side of S plane, and due to this one, the system would not be stable. That's why we say negative resistance is not suitable for analog applications. So in that work, we tried to remove the NDR effect, or we try to utilize the NDR effect so that the combined system could be stable. The pole should be in the left side of S plane, along with this is the one case. As the second case is if we can remove the NDR effect, like in general purpose. So also that we can use the negative capacitance based devices for analog designing.
Got it. Great work, Danshu. All the best. So, do we have any questions from the attendees? Professor Devdeep or someone else want to ask any question? Okay. In case we don't have any question, thank you, Danshu, and thank you, IT. We can definitely contact you separately for any other question that we may have, or the audience can directly contact you. And Professor Bulus and Professor Sudip Das Gupta is already available, always available. So we can move to the talk in that case.
Thank you, sir. Thank you, sir.
Thank you, Tanshu. Thanks for your time. So we have the next talk from IIT Guwahati. Siva Kumar will be presenting the next talk. He is the final year student of the Department of Computer Science and Engineering from IIT Guwahati. And he's a member of Mars Lab working on the performance optimization of non-volatile memories under supervision of Professor John Joseph at IIT Guwahati. And he will be presenting his work on improvising the non-volatile memory caches. And we all know that there are many techniques on the NVM memories, and big and small semiconductor leaders like Intels of the world are working on NVM memories. However, this work specifically covers the techniques to improvise the lifetime of NVM memories. So we may welcome Shiva Kumar from IIT Guwahati, and let's hear to him, and we can definitely ask any questions in the chat window, which may be taken up after the talk. Shiva Kumar, over to you.
Hi all, I'm Shiva Kumar, a research scholar from Indian Institute of Technology, Guwahati. I welcome you all to my presentation, Improving Lifetime of Non-Volatile Memory Caches. I will start with an introduction of my work, then motivation, and then I will explain about the proposed solutions, experiment setup, and results in detail. The volume of data that we are handling is increasing at a tremendous rate. As a result, our applications are becoming more and more data intensive in nature, and they demand for a huge amount of memory for processing. Our conventional memories such as DRAM and SRAM are inadequate to meet these requirements. This is basically due to their low packaging density and high leakage power. So the researchers across the globe started searching for an alternative alternative memory technology, and the non-volatile memory technologies such as STT-RAM, PCM, and RERAM came up as a promising candidate. So this table shows the comparison of our emerging memory technologies with respect to the conventional memory technologies, and if we see the features like cell size and standby power, we can see that our emerging non-volatile memory technologies perform better than our conventional memory. But in case of write latency and endurance, the performance of non-volatile memory is not as good as conventional memories. So let us discuss the issues with non-volatile memories in details. First one is the higher latency and energy for writes, and the second one is the limited write endurance. So what I will be concentrating more on the second issue, write endurance, in the rest of discussion. So what is write endurance? Write endurance can be defined as the maximum number of writes a memory cell can withstand before it's worn out. So how can we improve the write endurance of? So there are different techniques available. First one is write minimization techniques, in which we adopt different techniques to minimize the number of writes in the memory cell. And the second one is wear leveling, in which we try to uniformly distribute the writes across the memory. So I will be concentrating more on wear leveling techniques. So the figure shows the memory hierarchy of a system with two levels of cache memory. The level 1 or L1 cache follows split cache architecture. In the split cache architecture, both data and instruction will have separate physical memory, whereas level 2 or L2 cache follows unified architecture. There we don't have any such restrictions. So our focus is to replace SRAM based L2 cache with NVM. So the advantage of such a replacement is that because of the high packaging density of NVM, we can accommodate more memory cells in a given area than SRAM. Moreover, NVMs have zero leakage power also. So, but the problem with such an architecture is the limited write endurance of NVMs. So whenever there is an application with non-uniform write patterns, the memory cell tends to burn out faster, and it will affect the system performance. This emphasizes the need for a good wear leveling policy when we are trying to implement NVM in last level caches. The experimental studies show that there is a significant write variation between data and instruction blocks. In case of unified L2 cache, we have set variations across the set and also within the set. To analyze the write variation, we ran different benchmark workloads in a Unicore system in Gen 5 system. These benchmarks are taken from Spec 2006 workload suite. As shown in the graph, we found out that there is a considerable difference between average and maximum number of writes in the cache blocks. The write variations happens within a cache set is called intra-set variation, and whereas the write variation that happens across the set is called inter-set variation. So let us discuss about some of the existing works that are based on this wear leveling techniques for NVM. So I-square WAP is a technique that reduces both intra-set and inter-set variations using probabilistic line flush and swap shift techniques. Equal writes is another technique which try to reduce the intra-set variation and improve the lifetime by reducing the difference in number of writes among the ways of a set using a threshold value and counter. In dynamic window write restriction technique, the cache memory is divided into a set of equal sized windows, and the heavily written windows out of these is made as write restricted, and the selection of these restricted window is made periodically. Now we will discuss about our proposed work, virtually split cache. Our key idea is to logically split the unified cache into data and instruction cache. Logical partition is done at the set level in a waywise granularity. Each set is divided into instruction and dataways, and this mapping is interchanged periodically. So consider an 8-way set associative normal unified LLC, which is made of NVM. So in such a case, there is no distinction between instruction and data, as it is a normal unified cache. So now let us consider an set A of an LLC which is implemented using WISC. So here we have divided the data and instruction ways as in a 3:5 ratio. That is, 3 ways is exclusively reserved for instruction and the rest 5 are exclusively reserved for data. As we discussed before, instruction ways are less written when compared to data. So the database, and so the instruction ways will be comparatively less written. So after a prefixed reorganization interval, we will interchange this mapping, and this process continues periodically. Because of this, as a result, the heavy writes of database is distributed uniformly, and we can achieve ware leveling. Now we'll discuss about our experimental setup. We used Gemfile simulator to implement our model using Ruby memory model, and for coherence, we used Messy 2-level. We ran our architecture on Unicode, dual core, and quad core systems. L1 cache was used in split cache architecture, both I cache and D cache of 32 KB size and 4-way centricity. L2 cache, we used 512 KB size and NVM unified cache architecture with 8-way set associativity. Main memory was of 8 GB, and we took a benchmark from spec CPU 2006 suite. We categorized the benchmark into low, mid, and high based on their writes per kilo instruction value. Our switching threshold was, and data to instruction ware ratio was fixed experimentally, and we ran our experiment for 1 billion instructions. Now we will discuss about the results in detail. So this graph shows the result that we achieved for Unicore systems. The blue line shows the baseline architecture, which is the normal cache without any ware leveling techniques implemented on it. Orange one shows our proposed technique WISC, and the yellow one shows a state of our technique dynamic window write restriction. So from this graph, we can see that our technique performs better than the other two architectures. It gives 1.94 times better lifetime when compared to the baseline, and approximately 50% better performance when compared to DWW. Our technique was able to considerably reduce the intraset variations also. For the dual core systems, we categorized our benchmarks into low, mid, high, and low, mid, low, high, and mid, high. In low combinations, we ran 2 separate benchmarks from this category on 2 different cores. For low, mid, and low, high, we tried 1 benchmark each from 1 category on core. So in dual core also, we could achieve around 2 times better performance when compared to baseline, and approximately 20% better performance when compared to DWWR. In dual core also, we could achieve better performance in case of intraset. We could actually cut down the intraset variation for a considerable value. In quad core systems, we ran different benchmarks on 4 different cores. For low, mid, and high, we ran 4 different benchmarks on 4 cores, and for low, mid, low, high combinations, we ran 2 benchmarks from low and 2 benchmarks from mid category on each course. So in this case also, we could achieve better performance, but this performance improvement was clearly visible on low and low high. This is basically because in 4-core architectures, the write variations was low, so it kind of saturated for performance improvement. So this is evident from this intraset variation graph. We can see that intraset variations for mid-high benchmarks are low. That is why that is one of the reason for a comparatively lesser performance improvement in this case. Now we will discuss about an improved version of WISC that is named as dynamic WISC or DWISC. So while experimenting with different reorganization interval, we found out that some benchmarks with low MPK are working better for a low value of reorganization interval, whereas others are working with a higher value of reorganization intervals. So this actually motivated us to come up with a dynamic scheme which actually fixes the reorganization interval at runtime. So this is the architecture of the dynamic WISC or DWISC. So here we use a global counter which actually measures the write count for a given reorganization interval. So with this write count and a prefix thresh value, at runtime it will take a decision. So in our proposed model, we have used two reorganization interval, 1 lakh cycles and 10,000 cycles, and the write threshold as 100 and 1000. So based on this, it will choose one of the either combinations for the next time interval. So we ran the system, our proposed architecture on a Unicode system with the same architecture we discussed before. And we could achieve a better performance improvement than the WISC. With DWISC, we could achieve 2.14 times a better lifetime when compared to baseline, and when compared to WISC, we got approximately 20% of better performance. So intraset variation also, we could actually reduce it further from WISC. So this is the results. So to conclude, NVM are the potential candidates to replace the traditional memory, and we have a challenge of limited write endurance. Our proposed techniques, DWISC and WISC, could actually improve the performance. WISC actually improves the lifetime by 1.94%, 2.0%, and 1.72% for unicore, dual core, and quad core respectively. So these are some of the published and submitted works from these two works. So for any further discussion or clarification, you can always reach out at my email ID. Thank you.
Hi, Shiva Kumar. Thank you very much. Nice talk, and really good to know that some great stuff is going on at multi-core architecture Mars lab at IIT Guwahati under the guidance of Professor John.
Thank you, sir.
Comprehensive simulation results that is shown, demonstrated very nicely. Nice work on the virtual split cache. A couple of questions from my side first, then we may invite the questions from the audience.
Sure.
Currently, you have implemented your technique in the level 2 cache only, right? And
Yes,
what will be the implication if you want to implement the same technique in the L3 cache? Whether any changes will be required for carrying out the similar activity at L3 cache, or it can be simply replicated there without any modification or much modification?
Yes, sir. Only thing we can actually scale it out this technique to L3 cache also. So in L3 caches, what generally happens is the associativity is generally high on the higher side. So we have to fine tune that cache split architecture, like how many ways we have to reserve for instruction. Just fine tune it. This ratio 3:5, we have experimentally found that the best case scenario. We can actually work on that. Otherwise, we can actually directly work it on. It doesn't matter whether we are working on L2 or L3. It's scalable to different levels.
Okay. And is there any particular reason for having a better performance in dual core system when compared to the other two?
Yes, sir. We found out that there is a slight increase in performance when it's compared to the other two architectures like Unicore and dual core. We found out that it's basically because of the selection of workloads which we have made. So if the workload changes, the results also slightly vary. It will get almost a comparable result. That's the reason, which is slightly more is because of the workload distribution.
So basically, it's dependent upon the workload.
Workload distribution.
Very based on the workload also. Right?
Yes.
Okay. So I think we don't have any questions from the audience. If we have any questions from the chair or someone else, we can wait for a couple of seconds for them to ask this question. Okay. So in case we don't have any question, we can move to the next talk. Shiva Kumar, thank you very much.
Sir, there is one question.
It's a great discussion.
Yeah.
We would definitely like to reach you separately on your work. And I was always aware of that this work is going on at IIT Guwahati. Good to know here as well.
Okay, sure.
Thank you very much. There's one question from Nitanshu.
Yes, sir.
Which NVM has been used?
We are using STT.
Sorry?
STT RAM. Spin
Okay.
transfer.
Okay. Nitanshu, that addresses your query?
Yes, sir. Yes, sir. Thank you.
Thanks, Nitanshu. Thanks, Shiva Kumar.
Okay. Thank you, sir.
Thank you very much. Thanks for attending. So in that case, we may move to the third SRF talk, which is by Krishnendu. Krishnendu is presently a postdoctorate research associate in the University of Florida. He has completed his PhD from University of Calcutta as inspired PhD fellow from Department of Science and Technology, Government of India. And he received the Intel India final year PhD research fellowship from Intel India. And here today, he proposes a self-aware approach to deal with the existing issues in the runtime security. The proposed self-aware security modules work on a novel paradigm, which is going to explain, which can be incorporated in an SoC design without tampering the original IP and have the capability to learn and refine their actions with time. Really interesting work, and let's listen to him. So he will be talking on self-aware, nature-inspired approaches ensuring embedded security. So over to you, Krishnendra.
Hello everybody, my name is Krishnendu Guha and presently I am a postdoctoral research associate in University of Florida and I have completed my PhD from University of Calcutta under the supervision of Professor Amlan Chakrabarty and Dr. Debashish Saha. I was an inspired PhD fellow under the Department of Science and Technology, Government of India, and I also received the Intel India Final Year PhD Research Award. My PhD thesis is entitled as Self-Aware Nature-Inspired Approaches Ensuring Embedded Security. So, I'll be starting with an introduction, followed by the research objectives and research methodology, then the contributions. The first contribution is to bypass confidentiality attacks based on the crypsis behavior of geckos. The second contribution is to mitigate integrity attacks based on the defense against the parasitic breeding behavior of cuckoos. The third contribution is to counteract availability attacks based on the stigmergy behavior of insect colonies. The fourth contribution is to generate a self-aware authentication mechanism based on the identification strategy of ants. The fifth contribution is a symbiosis-enabled self-aware security mechanism for the execution of mixed critical tasks on reconfigurable hardware platforms. Then I will finally conclude and list the awards and publications related to this thesis. Introduction. So, system on chips are deployed in various arenas which are highly critical in nature and need short response time, like automobiles, medical IoTs, and several others. What is the problem? The problem is that the hardware Trojan horses may be implanted by adversaries in this system on chips during their design. Even illegal reuse and recycling of the system on chip components may take place, that is, the counterfeiting may occur. So, this jeopardizes system on chip operations at runtime, and replacing these SoCs at runtime is not possible. So, what can be a potential solution? The solution is to make the system on chip self-aware in nature. So, but how? For this, we basically adhere to the self-aware characteristics exhibited by different species of nature, because self-awareness is exhibited by various species of nature to ensure their survival in nature, and developing the self-aware SoC security techniques based on the intelligent security strategies exhibited by different species of nature can provide an efficient and alternative way to handle the problem scenarios. So, what are the objectives? Firstly, to analyze the potential threats. Secondly, to propose nature-inspired self-aware security algorithms. Thirdly, designing self-aware intelligent security modules that can facilitate runtime security and remove dependency on the golden models. Then, to incorporate intelligence, that is facilitating learning and updating of actions with time. Then, ensuring non-intrusive security. So, what is that? That is facilitating security without tampering of the procured IP components. And finally, to ensure high throughput and low overhead. Research methodology. Firstly, we have analyzed the problem scenario, then surveyed the various intelligent security mechanisms exhibited by different species of nature, and on finding a suitable analogy, we have proposed a self-aware nature-inspired approach to mitigate the related problem. Then we have demonstrated the proposed methodology with the aid of automata, because a proof by automata is universal in nature. Finally, we have implemented it and designed low overhead intelligent security IPs for mitigating the related problem, and we have also analyzed the overhead for ASIC and FPGA domains. So, our first contribution lies in generating a self-aware security mechanism to bypass confidentiality attacks, and this is based on the crypsis behavior of geckos. So what is the threat? The threat is that the secret information is revealed via side channels, and for our particular work the side channel is timing, and this takes place due to lack of synchronization at runtime. So the existing works are essentially algorithm balancing and masking, but these are intrusive in nature and are not self-aware. So we adhere to a crypsis behavior exhibited by geckos in nature, which essentially the synchronization at runtime. So geckos observe their environment and on deciphering a change, trigger their alpha melanophore stimulating hormones to synchronize their color. Based on this, we developed several self-aware security modules which essentially observes the runtime performance of their host, and on detecting a change in vulnerability in timing, essentially synchronizes the timing at runtime to prevent loss of secret information via timing analysis. So we demonstrated this via automata, and so these are our results where we obtain a very low overhead in area and power due to our security components, as well as the synchronization in timing is essentially maintained at runtime. So our second contribution lies in generating a self-aware mechanism to mitigate integrity attacks, and this is based on the defense against the parasitic breeding behavior of cuckoos. So what is the threat? The threat is that erroneous results is generated due to infected hardware trojans IPs. So this takes place essentially due to skipping of essential operations or due to performing of unwanted additional operations. The existing works follow a redundancy-based technique where triple modular redundancy is followed with majority pooling, but this induces low throughput and high overhead, and moreover, the fault diagnosis is not intelligent enough. So we essentially seek refuge to the defense against the parasitic breeding behavior of cuckoos, where the host bus tries to detect cuckoo eggs based on the side channels like color and size. Based on this, we develop self-aware intelligent modules which essentially monitors the operations of its host, and on detecting an anomaly performs intelligent fault diagnosis. That is, it does not perform triple modular redundant execution and majority pooling, but on detecting vulnerability based on side channel like timing, it reperforms the operation on some adjacent IP. This we demonstrate based on automata, and these are our results where we obtain low overhead in and high throughput. So our third contribution lies in generating a self-aware security technique to counteract availability attacks based on the stigmatic behavior exhibited in insect colonies. The threat is that sudden delays may take place at runtime due to delay inducing hardware trojans, and for this the real-time tasks may miss their deadline. The existing works are essentially centralized and do not focus on decentralized control mechanism where the low-level behavior of the individual IPs can be controlled at runtime to ensure the high-level objective of task completion within deadline. And for this, we adhere to the stigmatic behavior exhibited in insect colonies like ants or termites, where decentralized control mechanism via self-awareness is exhibited by members of the insect colony to ensure their high level objective of survival of the colony. And for this, we developed several low overhead self-aware security IPs that are essentially integrated to individual SOC components, and these IPs essentially monitors the performance and tunes the frequency of operation of its individual host, and this essentially facilitates us to obtain a decentralized control mechanism within the self-aware environment of the SOC that we develop. And we demonstrate this by automata, and these are our results where we obtain low task rejection rate. Our fourth contribution lies in generating a self-aware authentication mechanism based on the identification strategy of ants. So our system over here is essentially a remote FPGA platform where the hardware IPs needs to be sent from distant source, and the threat is that adversaries may intercept the IPs during their transmit, and they may send fake IPs to the remote FPGA platform, and if these fake IPs configures the remote FPGA platform, then the control may pass on to the adversary. So the existing works are subjected to brute force and machine learning, and also they do not exhibit a zero knowledge verification mechanism. And for this we adhere to the identification strategy exhibited by ants in nature. So what happens is that the ants of a particular colony possesses unique cuticular hydrocarbons, and the signals emitted from these cuticular hydrocarbons is unique for that particular colony, and these cuticular hydrocarbons differ with members from another colony. So when ants only allow their own members to enter and prevent entry of intruders via sensing the signals emitted by the cuticular hydrocarbons, which actually differs uh, between members of another colony. And based on the cuticular hydrocarbons, we essentially develop a proof of authentication module which is associated with the intellectual properties developed from a particular source. And as the proof of authentication module differs from source to source, hence their signals emitted or the side channel characteristics for our case emitted will also be different. So we demonstrate this by automata, and we obtain a self-aware authentication mechanism where we can prevent entry of fake IPs to the remote FPGA platform, and we also ensure a zero knowledge authentication mechanism via this method. So our fifth contribution lies in generating a symbiosis-enabled self-aware security mechanism for the execution of mission-critical tasks on reconfigurable hardware platforms. So over here we have a multi-FPGA environment, and each FPGA is associated with executing several critical tasks which may either be high critical or low critical, and these critical tasks are essentially executed in the form of several task schedules. The threat over here is that the hardware Trojan horses may be present in either the FPGA fabric or in the bit streams that are essentially associated with the task executions, and this may jeopardize the task schedules. So the existing problems are that the existing works essentially do not focus on this multi-criticality aspect, and if and also induces high overhead and low throughput when all the security elements are loaded in a single environment. So we essentially adhere to symbiosis. So symbiosis is essentially mutual help, and this facilitates the cooperative execution of tasks, which reduces the overhead and increases the throughput. So what essentially happens over here is that we develop several self-aware modules which are essentially associated with different FPGA platforms, and if it finds that its own FPGA platform is anomalous, then it outsources the task to other self-aware modules to be executed in other FPGA resources. So essentially the high critical tasks are given preference, and if after completing high critical tasks time and space exists, then the low critical tasks are executed. So these are our results and solutions. So effectively we get a higher throughput, and the task rejection rate for the non-periodic tasks decreases, and the task success rate for the periodic tasks increases, and even the overhead we get, and for overhead also we get a low overhead for the security modules which we have developed. So to conclude, we can say that in this thesis work we have proposed several nature-inspired self-aware approaches for embedded security, and low overhead of our proposed security modules over standard benchmarks support their use for practical applications, and the future use of these proposed techniques is being carried out for reconfigurable hardware-based cloud platforms, and this is being done with association with Intel India. And for the awards and acknowledgement, I thank the Department of Science and Technology, Government of India for the Inspire Fellowship Award, the Intel India Final Year PhD Research Award, and I also received the VLSI Design 2018 PhD Forum Second Runners Up Award for the ongoing works. So these are the publications thesis related. So we have an entire full authored book, 5 journals, and 8 conferences, and also a IEEE India Council newsletter. So thank you everybody.
Thanks, Krishnendu. Nicely summed up all your 5 techniques towards this self-aware, nature-inspired approaches for embedded security. I wish all the best and looking forward for continuing your work coming back to India.
Yeah.
I have a couple of questions here. So, plan to apply the real-time security techniques on non-periodic tasks for your resource-constrained platforms?
Yeah. So basically what happens, we have mostly done our experiments on periodic tasks, but when it comes to non-periodic tasks, this does not have a pre-decided arrival time and its deadline, right? So when the system is resource constrained, we do not have enough of space. So the challenge over here is that we need to find out spaces from the periodic task schedule and try to fit it by increasing the frequency on and all this aspect parameters. So this is an aspect where we need to focus on and try to fit in or squeeze in the non-periodic tasks in the periodic task schedule and ensure their completion within deadline. And there that the symbiosis will come into quite effect over here, because the periodic task schedule is quite compact, and squeezing them the non-periodic tasks into the periodic task schedule in a single FPGA platform will not be possible. Therefore, the agents will come into the scenario. The agents will be outsourcing the task to other agents, and over there they will follow the symbiosis and ensure the completion of all the non-periodic tasks, right?
And one more question, can these techniques be replicated to handle the attacks on reconfigurable hardware-based cloud and edge platforms?
Yeah, so basically this is what we were working on after I submitted my PhD, and we worked with this with Intel, right? So in this edge and cloud platforms in this industry 4.0 era, these are appended with all these FPGAs and all these things, right? Now what happens is that the attacks may take place. Now what kind of attacks are there? This leakage of side channels, these are all there. But another important attack when it comes to this cloud and edge platform is that the multi-tenant attack, that when all the users are working on, right, every user will not be genuine, some users will be malicious, right? And this is where this self-aware characteristics comes into place, that if some user is malicious, then how we can detect it, then what kind of malicious tenant, or what how this malicious tenant behaves, and at runtime how we can detect the activities of this anomalous behavior and then ensure security from them. So this type of works we are working with Intel, and this year also a paper came out in VLSI Design 2022, where we focus on this row hammer attacks of multi-tenant systems, and we try to mitigate it with the self-aware nature, and this was published in this VLSI Design 2022. Yeah.
Okay. Thank you very much. Do we have any questions from the participants? I think no. We may wait for a couple of seconds and then we can proceed. Okay. I don't think that we have any questions. So in that case, thanks Krishnendu for your talk. Yeah. And we can proceed ahead with the next talk. Thank you very much for joining us today. And great elaboration of your work. We will definitely contact you separately if any other information is required. Thank you very much.
Yeah. Thank you.
Bye. So with this, we are moving to our last last talk from Alicia. She is doing a PhD at Kochi University of Science and Technology and has over 2 years of research experience in satellite image processing at Indian Space Research Organization, ISRO. And currently she's exploring the spintronics-based devices and optimization of many and multi-core architecture. And today she will be going to propose an efficient TRNG implementation, which is based on the reduced retention time. Her approach offers high throughput, lower energy dissipation per bit, and improved NIST test criteria compared to the state-of-the-art spin-based TRNGs. And the title of the talk is Reduced Retention Time. I mean, it's voltage gated spin orbit torque random access memory, 2 random number generator for on-chip designs. So over to you, Alicia. I request you to present your talk, and we can have the Q&A sessions later after this talk. Thank you very much.
Good day to one and all. I am Alicia from Department of Electronics, Kochi University of Science and Technology. I will be presenting my abstract titled as Reduced Retention Time Voltage Gated Spin Orbit of Random Access Memory true random number generator for on-chip designs. Overview. Moving on to the introduction. Random numbers plays a critical role in modern information technology. Random numbers used in encryption algorithm for digital signature and to generate uncracked cipher text. Recent development, deep learning and neural network leads to a new scope in applications of random numbers. Random numbers used for control the behavior of artificial neurons and synapses to reduce the computational power. Here comes the classification of random numbers generator. Random number generator are broadly classified into zero random number generator and true random number generator. Zero random number generator are based on a particular algorithm. They are deterministic and predictable. So it cannot be used for the security applications. Here comes the importance of true random number generator. The true random number generator is broadly classified into CMOS devices based and spintronics based. In CMOS based devices, the randomness is generated artificially in terms of thermal noise and jitter. But in the case of spintronics, the magnetic tunnel junction based devices such as STT-RAM and SOT-RAM are used. In compared to SOT-RAM have high efficiency in STT-RAM. The true random numbers generators is a function or device based on unpredictable physical phenomena called an entropy source that is designed to generate non-deterministic data to seed security algorithms. So here, the block diagram of TRNG. We have entropy source, entropy extractor, and post-processing. The entropy source and entropy extractor determine the quality of randomness. And due to the physical interference and the correlation of output, the randomness of output will be reduced. In order to enhance this output, we go for the post-processing techniques. There are two major techniques out there, von Neumann techniques and XOR corrector. So our objective is to design an energy efficient and highly throughput spintronics based true random number generator for on-chip applications. Here, the diagram shows a CMOS based TRNG. We have a noise source and an amplifier, and the bit stream is generator. So here, the artificially created the randomness. This leads to low bit generating rate and high area and power overhead. So we need an alternative mechanism which have high throughput and high energy efficiency used for next generation applications. Here comes the spintronics based TRNG design. The key element of spintronics based design is magnetic tunnel junction. Here we can see the tunnel junction is consisting of two ferromagnetic layers and a oxide layer. Depending upon the magnetization of these layers, we can set as a parallel state and anti-parallel state. There is an energy gap between the parallel and anti-parallel states. So this way, the MTJs have inherently randomness property. It's the switching within a 10 nanosecond and 100 femtojoule per each bit of generation. So these properties like high write endurance, high speed probability switching, and high throughput guarantees MTJ based TRND design for next generation applications. Here, three different categories of spintronics based TRND designs. First is switching time dependent stochasticity. Here we can see the comparator is continuously monitoring the state of MTJ, and depending the outputs of counters and oscillator, we can improve the randomness. Next is peripheral current correction circuit. Here there is a current feedback path is there here. So depending upon the correction logic and current controller, we can modify the MTJ's current and obtain better randomness. Next is parallel design MTJ cells. Here, the parallel arranged design of MTJ, we can improve the stochasticity of the MTJ switching. But in these technologies have high area and power overhead and also very complex process, and also we need much time and delay is required. So we need an efficient design which have high throughput and high energy efficient. So we design a reduced retention time VGSOT TRNG. Here combine the effect of voltage control magnetic anisotropy and reduce retention time. The VGSOT is an advanced form of SOT RAM. Here we are adding a particular voltage to the MTJ cell. So adding the voltages to the MTJ, here we can see the switching probability of MTJ. So the drastic switching occurs. Here the telegraphic switching profile of MTJ is shown in this figure. Here this is the VGSOT RAM. The VGSOT RAM, by applying a voltage into the MTJ cell, we can reduce the energy barrier between parallel and anti-parallel state. So this way we can obtain 20% of reduction in write current and 45% reduction total energy compared to SOT RAM. Next is reduced retention time. The retention time is coined as the time for which data can be held in a memory cell in the absence of external power source. The diagrammatic representation of retention time versus energy barrier. So retention time is reduces, energy barrier is also reduces. This reduced retention time VGSOT is modeled in a Verilog A using the Karen's Virtuoso platform. So the reduced retention time is directly proportional to tunnel magnetoresistance. So by configuring the geometrical and physical properties like oxide layer thickness and TJ dimension, we can control or tuning the retention time. The main advantage of reducing retention time is we can obtain any without any structural variation and peripheral overhead. Results and discussion. The quality of randomness of this design is tested using NIST statistical test suite. Here it contains 15 tests and each test get a p-value. If the value is greater than 0.01 and the test will be passed. So we compare the NIST test with STT-TRNG, SOT-TRNG. Here we can see the result is not passed, but with the post-processing or current correction logic, we get the proper results. But when we are comparing VGSOT-TRNG with the other TRNG design, here we can see even though the randomness improved compared to STT-RAM, the results, the test result is not passed. So we go for reduced retention time VGSOT-TRNG. Here we can see without any current correction logic or any other post-processing units, RRT VGSOT passed all the tests. Then we next go for the post-processing with the XOR character. Here we can see the p-value is improved, which shows that randomness improved using the post-processing. Performance analysis. First we go for throughput. Here we can see the RRT VGSOT have 20% of improvement in throughput as compared to other previously TRNG designs. Next is energy consumption per bit. Here we can see on an average 33% of reduction in energy consumption in the case of RRT VGSOT compared to previous technologies. So NIST test passing rate is 100% in case of RRT VGSOT. The main attractive for this design is area. Here we can compare the area of conventional CMOS devices TRNG with RRT VGSOT. Almost 80% of area is reduced. Move on to conclusion. Proposed reduced retention time VGSOT TRNG design, we have increased 20% of throughput and reduced the energy consumption by 33%. It's improved the NIST test criteria. The design provides better randomness without any feedback, peripheral circuitry and post-process, so we can increase the area efficiency. This enables the use of spintronics-based TRNG in high performance and low power computing applications such as AN, stochastic computing and IoT devices. Thank you.
Thank you, Alisha. I think I'm audible to you. And thanks for your presentation. Yes, just out of curiosity, so you are currently employed at ISRO and doing your PhD at QSAT?
Yes, sir. I'm doing my PhD in QSAT.
And at the same time, you're employed at ISRO, right? You're taking study leave there, right?
Sir, I didn't get you.
Okay. Let me move to my question directly. Okay, there are two questions. Why did you limit the retention time to seconds range in the design?
We go for first we go for the Monte Carlo analysis in PVT variations, and we reduce the retention time below the seconds range. So it's a very high in PVT variations on there. And next we the read disturbance error and expedition misses and all of these errors will be increased when we are limiting the retention time in nanosecond and microseconds range. So optimal performance is getting in seconds range. That's why we limited to seconds range.
Okay, and how did you model this VG sort with the reduced retention time? Let me repeat if it's not okay.
So first we configure the. It's okay, sir. It's okay. It's audible. First, we based on LLD equation. First, we model the model it in a cadence versus a platform, and after that, we go for parametric analysis. Each parameters like MTJ thickness, free layer, oxide layer, thickness, etc. And then we go for the area analysis using NVC simulator. In the system level analysis done by GEM5 simulator. And we have to analyze the switching probability, and this is done by object-oriented micromagnetic framework.
Okay, let's see if we have any more questions in the chat from the participants. I don't see any. We may wait for a second if someone wants to ask any question, and then we can proceed further. Okay, in that case, Alicia, thank you very much for joining today and presenting your work.